So I'll talk about the affective disorders and how this relates to deuterium concentration. Now, when we considered affective disorders, this includes anxiety and depression. And the primary treatment for affective disorders currently is serotonin reuptake inhibitors. Now, as most of you probably know, the serotonin reuptake inhibitor blocks the serotonin transporter and thereby increases the amount of serotonin in the synaptic cleft and also the duration of time that serotonin stays in the synaptic cleft. Now, the problem with SRIs is even though they are very effective, they are not effective for all mood disorders or affective disorders. One of the reasons for this is because some mood disorders don't result from less serotonin. This actually can happen when there's too much serotonin. So what's interesting about the serotonin transporter is it contains a polymorphic region. And this polymorphic region rises of two different types of the allele. The main is the short allele and the long allele. And what we get with these two types of the allele is the short allele has less transcription for the mRNA. And due to this decreased transcription of the mRNA by the short allele, we have less serotonin transported at the synaptic cleft. So individuals who contain the short allele, and this is about 30% of the population, they actually have an increase of serotonin at the synapse. And this makes them susceptible to actually stress-related disorders. So what we see here is in clinical studies, we have individuals that are, homozygote for the short allele of the serotonin transporter, individuals that have both the short allele and the long allele, and then of course we have the individuals with only the long allele. And what happens with these individuals is when they experience stressful situations, they have, susceptible to the stress. So individuals that have only the short allele, the more stress they receive, they have greater incidence of depression. And this is true for many things. So this is how they themselves feel. This is the diagnosis of depression. And what's really shocking here is if you look at the individuals that only have the short form of the serotonin transporter, is they have a very high rate of suicide. Now, what's important about this is when you give these individuals a serotonin reuptake inhibitor, this actually increases the suicide rate for these individuals. So obviously, we need other methods for treating this. Now, the way we are working is we have a knockout animal, and the way we create the knockout animals, you have your vector gene, and on each side of the vector gene, you have a monomerase DNA to the gene you want to target. And basically use recombination, and you take out the gene you want to target with your transcription factor here, the neo cassette, and then you take out the gene. And what you do is you screen your embryonic cell lines for your target gene, and then you implant your blastocytes into surrogate mothers, and at the end you just breed your offspring. And then at the end of this, you get your knockout mice. So what we have is we have a serotonin transport knockout animal, and here we have the transcription factor, here the neocassette, and they knock out the number 2 exon of the gene. And in the bottom, we have the embryonic stem cells, shown we have the heterozygous, as well as the knockout animals. And here is actually the DNA test of the mice. So what we're doing is what's important with these animals is when you look at their phenotypic features, they are very good for what you see in the human situation in terms of anxiety and depression. So as the people who have only the short allele, these animals as well are more sufficient to anxiety, learn fear, aggression, they decrease in aggression. Or the heterozygous animals, they are missing some of the more robust problems of the short allele. But what's also very interesting with this is for us, we're primarily interested into the depression, but we also start to look at into the metabolism and the glucose function for these animals. Because what you can see here is the animals that have a double knockout, so they're completely missing the serotonin transporter, they have a complete increase of glucose, leptin, cholesterol, and triglycerides, as well as they have the increase in body weight, glucose tolerance, insulin sensitivity, so they're insulin resistant, and they have a decrease in brain glucose utilization. So this means is they have metabolic problems in the brain. And when you look at the phenotype, this is quite similar to people who have a diet-induced obesity. So through the age of these animals, only the total knockout animal has a complete increase of the body weight. And as well as you look at the complete knockout animal, you have leptin resistance as well as insulin resistance. Now for today, we'll only be looking at the heterozygote animal. And the reason we're only looking at the heterozygote animal is because we're mainly interested in only the affective disorders. And in this graph, what is quite interesting, as you can see, this is taken from data from the United States, is here we have the parts per million of the deuterium concentration of water for each state in the United States. And on the y-axis here, we have the amount of depression in the United States. And you can see we get a nice correlation with the amount of deuterium and the rate of depression of the individuals who are influenced by this water. And here on the top, you have the depression, and here on the top, you have the individual states with the deuterium content. Now, what's also quite interesting with this is when you look at the diabetes for this same area, you also get a nice correlation in the terms of diabetes and the concentration of the deuterium. And this is really significant for any deuterium concentration above 150 parts per million. People who are in these areas with such water, they have a very highly significant increase of diabetes. But for today, I'm going to show you some preliminary data we have concerning the heterozygote knockout animal. And because this is our preliminary data, we're not doing any forms of stress to the animal. Normally we do stress, but for this is just to look at the condition of the light water treatment. So it's a very simple experiment. We only have the two forms of light water. We have what we're calling our controlled light water, but it's actually quite heavy. It's at 155 parts per million. And then we have our treatment group, which is the light water at 91 parts per million deuterium. And then we're using citalopram, which of course is an SRI, as a positive control. And we're giving it at the typical treatment of 15 milligrams per kilogram a day. Now, I'll briefly go over the behavioral test before I show the data. And then because we also have this change of metabolic syndrome for these types of animals, we also did a glucose tolerance test. The first thing we did is we looked at the forced swim test, and we have a modified version of this. And we include a third session 120 hours after the second session. And this allows us to look at brain plasticity, but this is an ongoing experiment, so today I'm going to be looking at the behavior. And as you can see, the animal will quit swimming here, and here now they swim. So what we look at is the duration of swimming, the amount they swim, and when they first stop swimming. So when you look at the data here, we have the 155 parts per million light water, and we have the 91 parts per million light water. Now for the latency to floating, the light water very significantly enhanced the wild type group. So this is a positive effect that this is anti-anxiety, but this was only in the wild type animals. Now later on you'll see today that we have no correlation for anxiety with deuterium water. But still, even though it's not significant, it does have a slight effect on the knockout animals. Now in the second and third session, we don't expect to see anything because if you have an increased latency here, it means the animals have a very bad cognitive deficit, but of course we don't have this and we're not expecting this. Now what's also more important here is the duration of floating. So the amount of time that they just spend floating and not swimming. And again, I'm guessing because this is kind of also stressful for these animals, and these mice are susceptible to stress, they're actually performing a little better than the wild type here. Now this is two-way ANOVA analysis, and here the significance, I have to point out, is only for genotype. So this is not for treatment. So here light water didn't have a significant effect, and here the control animals have more significant floating compared to the heterozygous. But still you can see we have the trend for the light water to be beneficial. Now, the next thing we looked at is this novel cage exploration, because individuals who have depression, they don't try new things, they're not interested in new things, they have low ambition, basically. And when we do this, we have a positive effect for the light water treatment in both the wild type animals, as well as the animals that only have one allele for the serotonin transporter. And of course, as we would expect, the wild type animals overall are better than the animals that are susceptible to stress. And again, here we have a positive effect of the light treatment. So here we have the light water treatment increasing the motivation for these animals to explore. Now again, with the novel object exploration, we just are similar to the novel cage, but instead of a new environment, we place an object that's unfamiliar to the animal inside their cage, and we look at how often they explore this object. And here we only had a treatment effect only for the knockout animals, for the heterozygote animal. And as you can see, again, the light water at 91 parts per million significantly elevated the animal's desire to investigate the new object. Now we also have another recognition test, and this is quite easy. We have a glass cylinder, and we place the glass cylinder basically against the wall, and it's on a table that's at least 1 meter above the ground. Now inside the glass cylinder, you put two objects, and one you put close to the wall, and one you put close to the edge of the table. And what happens is normal mice, they will spend about the same amount of time between both objects. While mice that are more anxious or depressed, they will stay more towards the safe area by the wall. And then on the second day, you replace this object, and then you look at the amount of time they explore the new object. Now, depressed animals will stay only here, and they don't care about the new object at all. Now, when we do this in our animals, we can see that the light water treatment significantly enhances the time that the animal spent recognizing the new object on the second day. So again, this is ameliorating the depressive traits of these knockout animals, of these heterozygous animals, I have to say. And then again, we have the dark light box. This is another test mainly for anxiety, and it simply have a dark compartment and a light compartment. You put your animal first in the dark compartment, and then you measure the time it spends in the light, the amount of times it goes back and forth, and this is at 25 lux, so here it's not very bright. Sometimes it's at 100 lux, but here we're not doing a stress design. This is only to look at the effect of deuterium water. So here we have 25 lux. And when we do this, for the latency of exit, so the amount of time it takes the animal to go into the dark side, unfortunately we have an increase for the light water treatment. But the main parameter for this experiment is the time spent in the box. And the time spent in the light box, there's no difference here. So this is showing that neither group and the treatment had no effect on anxiety-related issue for these animals. And the only effect we ever see for citalopram in our results is in the number of exits. So in the animals that have too much serotonin and now have even more serotonin due to the citalopram are becoming hyperactive, basically. And then at the very end, we did the glucose tolerance test because we were interested in the effect of the metabolism. And for this, we fasted animals for 18 hours, and then we just did an IP injection of glucose at 1.5 milligram per gram. And as you can see, for the wild-type animals who received deuterium water, they had a better utilization of the glucose at 15 minutes and again at 30 minutes. And there's no effect on the basal level of glucose for this. And in our cert animals, so the heterozygous animals, so for the transporter, we only had an effect at 30 minutes, but still it's quite good. Now I have to say these are not stress, and later on we will do the stress experiments. And when we do so, we expect to see better results for the cert animals for light water. So to summarize this, animals who are missing the serotonin transporter show lower cognitive performance and a little bit more anxiety. And we expect this to be more symptomatic when we stress the animals. And here we have the effect of light water is good in both animals, but because the animals are not stressed, it's better in the wild-type animals. Now, when we apply stress to the animals, we're expecting to see a better effect of light water on our cert animals. And again, the preliminary data shows that there's a promise for improved glucose utilization when the animals are exposed to lower concentration of deuterium. So I'd like to acknowledge the people involved in this aspect of the experiment. Dr. Lesh provided us with the transgenic mice with the knockout animals. Stepla Clover is responsible for designing the behavior experiments primarily. And the majority of our behavior is conducted in Lisbon. And these are the people who organize our organization there in Lisbon. So thank you.